morning students. Today we will discuss about hyperfine structure of spectral lines. So we have already studied about fine structure of spectral lines. The fine structure is due to spin orbit interaction of the electron. That is, electron is having spin motion and angular motion. Then there is a corresponding spin angular momentum and the orbital angular momentum. The interaction between these two leads to fine structure of spectral lines. So what is hyperfine structure? Now what this is also the hyperfine structure. What happens is that the lines will split up into a more number of lines. That means instead of a single line, you will be seeing a large number of lines. Such a type of spectra is actually known as a hyperfine structure. So the hyperfine structure originates from the coupling between the coupling between the nuclear spin magnetic moment and the electron magnetic moment. That is, coupling between electrons spin as well as orbital angular momentum and the nuclear magnetic moment, that is mainly due to spin of the nucleus, and usually nuclear magnetic moment is known as nuclear spin magnetic moment. So nuclear spin angular momentum, and this interaction is actually responsible for the hyperfine structure of spectral lines. So to distinguish between fine structure and hyperfine structure, fine structure is mainly due to the interaction between the electron as well as the electron spin as well as orbital motion, and hyperfine structure, it comes to interaction between the electron's total angular momentum with the angular momentum of the nucleus, that is mainly due to spin. There will not be any distinction between spin and orbital in case of nucleus. So nucleus, usually the nuclear angular momentum is represented in terms of I, and I equal to root of I into I plus 1 into H cross. If you look into some books, the square root of I into I plus 1 is simply put as I star. So instead of this expression, they will be using I star H cross. Both are same. And here I stands for the nuclear spin quantum number. The coupling of spin angular momentum with electronic angular momentum leads to a splitting of energy levels. So this gives rise to multiple structure to the spectral lines, and this is actually known as the hyperfine structure. Now, the total angular momentum vector here, between the coupling between the electron angular momentum and the angular momentum of the spin actually gives a total angular momentum, and this is usually denoted by the symbol F, and this F is equal to sum of I and J. I, it is the nuclear spin quantum number, J is the angular momentum of all the electrons. Now I have shown the coupling is shown with the help of a diagram. Here actually this is S and S, and this is L. So the coupling between S and L give rise to J, that is shown here. So this is a classical expression. So here you can see vectorial addition. This is the direction of L, this is the direction of S. So the resultant will be along this direction. So if you complete the parallelogram like this, then the diagonal will give you the direction of J. So this is the direction of J. Now the J vector is this way it is processing, and this is the direction of I, and this gives the resultant F. I and J coupled to give F. So this is what is represented in the figure. Now F can also be represented as square root of F into F plus 1 into H cross, and F can take values J plus I to modulus of J minus I, that is 2J plus 1 values. So the transition rule is governed transition. So once the splitting is occurred, now the transition between various levels is according to selection rule. The selection rule is delta F equal to 0 plus or minus 1. Either it can be 0 or it can be plus 1 or minus 1. So this transition is responsible for the multiplicity of the spectral or the expanded view of the spectral lines or the structure of spectral lines. Now interaction energy, I am not deriving the interaction energy. So simply it is a by 2 into f plus 1 minus I into I plus 1 minus j into j plus 1, where a is a constant. Often the HF means typified structure quantum number, is written as a left subscript. That means here 2 stands for example 2d pi by 2, and if f is equal to 3, then it is represented as 2d pi by 2 3. 3 below, just below 2. It is represented. Here 2 multiplicity j, this pi by 2 is capital J and f is nothing but 3. As an example, we will consider the case of bismuth atom. Consider 2d pi by 2 term in the bismuth atom where j equal to pi by 2 and the observed I is 9 by 2. So the allowed values of f are 9 plus 5 by 2, that is 9 plus 5, 14 by 2, that is 7. The minimum value is 9 minus 5 by 2. So this is nothing but 4 by 2, that is 2. So the allowed values of f are between 2 and 7. They are 2, 3, 4, 5, 6 and 7. So that means 6 values are possible. 2 into 5 by 2 plus 1, 2 and 2 get cancelled, 6 values are possible. Now Eij can be calculated using this relation. If you substitute here the values, then you will get the various energy states, various interaction energy terms like this, and you can plot it like this. So there is a plus term, then there is a minus term. These are the terms 7, 6, 5, 4, 3, 2. Corresponding to the interaction energies are like this. The states are shown here: 2d pi by 2 7, 2d pi by 2 6, 2d pi by 2 5, 2d pi by 2 4, 2d pi by 2 3, 2d pi by 2 2, like that. So actually this needs only qualitative description, so we don't have to go into the derivation of the details of the hyperfine structure. So last year this was a question, university question, so study well. Thank you.